We're going to continue with chapter 6 and move into exponential functions. So chapter 6, we're looking at exponential functions now. So we want to determine if the tables that are listed here represent a linear or an exponential function. So when we're talking about a linear function, back from a couple chapters ago, we know that a linear function is in the form y equals mx plus b. And we know that a linear function has a constant rate of change. So that means that our x's are increasing by the same amount each time, but more importantly, our y's are going up or down, addition or subtraction, by the same amount each time. So when we think about linear, we want to think of a plus or a minus with our y's. When we're talking about an exponential function, we're talking in the form y equals a, and then in parentheses, b to the x power. So it's exponential because it's being raised to a certain exponent. In this case, we have a common ratio or constant factor. So we're being multiplied by the same amount each time. So you want to think of exponential as multiplication. And you want to think of linear as addition. So we're looking at our y values and we're looking at what's happening here. I always start with addition because that's easier to do. So if I go from 2 to 4, I'm adding 2. And then from 4 to 6, I'm adding 2. And then from 6 to 8, I'm adding 2. So because I'm adding the same amount each time, I'm not multiplying by the same amount, right? 2 times 2 is 4, but 4 times 2 is not 6. This represents a linear function. It represents a linear function because we have a constant rate of change. My y's are increasing by the same amount each time. If I go to the next example in B, if I try addition, 4 plus 4 is 8, but 8 plus 4 is 12. I'm really going up by 8 each time, and then I'm going up by 16. So it's obviously not linear, okay? It doesn't have the same constant rate of change. I went up by 4, and then I went up by 8, and then I went up by 16, so it's not linear. So I say to myself, okay, let me try multiplying. So 4 times 2 is 8, and 8 times 2 is 16, and 16 times 2 is 32. So we have what's called a constant factor here. We're multiplying by 2 each time. So you're looking at the relationship between your y values to determine, am I multiplying by the same amount each time? Am I adding by the same amount each time? And that will determine whether it's a linear or an exponential function. In example 2, we're given both exponential functions here, and we're just simply asked to evaluate. When we're asked to evaluate, all we're asked to do is just plug that in for x and see what we get. So if we look at example A, all I'm going to do is I'm going to take that 3 and I'm going to plug it in for x. Now it's important that you get your order of operations correct. Remember, exponents come before multiplication. So we shouldn't be multiplying -2 times 5 to get -10 and raise it to the x. We have to take that 5, raise it to the third power, and then multiply times -2. So we're going to get y is equal to -2, and then in parentheses 5 raised to the third power. I have to do this 5 to the third first because exponents come first. So this is coming first. So 5 to the third power is 5 times 5 times 5. So 5 times 5 is 25. Times another 5 is going to be -125. And then take that and multiply it by -2, and you're going to get a y value of -250. Same idea here on the second example. Take that -2, plug it in. Y is equal to 3, and then 0.5 raised to the -2nd power. You can use your calculator to do this, or if you want to think about this by hand, this is really 1/2 to the -2nd, which ends up being 1 over 1/2 to the second. So you end up getting, or 2 to the 2nd power, you end up getting 4. So we have, and again, you can just put that in the calculator. Y equals 3 times 4. So your Y value is equal to 12. So pretty easy here on these two examples. All you're doing is you're just plugging in for X and you're evaluating. Just make sure that you do your order of operations correct, exponents before the multiplication. Save to try these for class. Core concept here, we're looking at the graphs of exponential functions. Notice in your graph on your left, this is what the graphs when b is greater than 1 look like. Those are what we call exponential growth graphs because they're growing as your x value increases. Either they're growing in the negative direction or the positive. And then you can see on the right-hand side, so these are growth. These are what we call exponential decay graphs because as we increase our x value, notice that they're getting closer and closer to 0. So just two general ideas of the graphs for you to look at. Now we're going to actually graph some of these. So we want to graph 4 times 2 to the x. And we want to describe the domain and range of this graph. So when you're graphing an exponential, the easiest way is to create a table of values. And the most common x values that we use, similar to that we've done in the past, are -2, -1, 0, 1, and 2. I know this is going to be an exponential growth graph because this value here, b, is greater than or equal to 1. Or greater than 1, I should say. So the general form of an exponential, remember, is y equals a times b to the x. I want to just show you something that's going to be interesting that we're going to see, but we're going to create a table of values here. So all I'm going to do is I'm going to plug in that x value plug in the x values of -2, -1, 0, 1, and 2, and see what I get for my y values or f of x. Notice that they've written this in function notation, but it doesn't matter. It's the same difference whether you write it as y equals or whether you write it in function notation. So if I plug in -2 in for x right in here, and I evaluate, I'm going to get a y or an f of x value of 1. Continue to plug in. You're going to get 2, 4. When I plug in 1 for x, 2 to the first power is 2 times 4 is 8. And then when I plug in 2, I'm going to get 16. So let's take a look and plot this to see what it looks like. So -2, 1, right there, -1, 2, 0, 4, 1, 8, and 2, 16 would be off my graph. This is an exponential graph. So remember the shape, and the shape is important. So we're going to look like this blue graph right in here on this one because our a value is greater than 0 and b is greater than 1. Our a is 4, our b is 2. So we're going to have a graph that looks like this. Notice that an exponential graph is not linear. Okay, you might have heard a lot of things about, like when we've been dealing with this coronavirus, that it's growing exponentially, meaning it's growing much more rapidly than a linear graph would represent. Now, in describing the domain, your domain for all of these exponential graphs is going to be all real numbers because it can take on any x value. So however you want to write it. Your range in this graph, if you notice here, this graph has what's called an asymptote at the x-axis. It never reaches the x-axis. It gets really close to it, but it never actually reaches this x-axis here. So if you take a look here, right, it never reaches this. Gets close, but it never gets there. Our range is any y value greater than 0. So your range is y is greater than 0. I want to just briefly illustrate two important things when we're looking at this function that hopefully maybe you picked up on. This 4, this number right in here, if we take a look at that, notice that this 4 is really your y-intercept. And this 2 right in here is the constant factor. It's what you're multiplying by each time. So you actually sort of don't really even need to create a table of values here, because if you just say, okay, notice there's my y-intercept at 0, 4, and then I just multiply by 2 each time, and that's how I got the other points in my graph. So there is a relationship there between both of those pieces, similar to what you would see in something that's linear. Let's look at our next example. F of x equals 1/2 to the x. So notice here, actually, we're missing our, if we think about y equals a times b to the x. We don't have this part right in here. But let's create our table of values and see what it looks like. So again, I'm going to use my basic -2, 0, 1, and 2, because those are the easiest ones to use. You can use the calculator to help you get your table. That's perfectly fine. So when I plug in -2, I'm going to get 4 for my y value. Notice this is my constant factor, so I could just multiply each of these by 1/2, which is the same thing as dividing by 2. So I'm going to get 2. I'm going to get 1. I'm going to get 0.5, or 1/2, and then 0.25. And notice here, I said there wasn't really an a. Well, there's really like a 1 there. That's really my y-intercept, and you can see there it is right there at 0, 1. So let's plot this one. We've got -2, 4, which would be right there. -1, 2, 0, 1, 1, 0.5, 2, 0.25. And you end up getting a graph that looks like this. Once again, your domain is always going to be all real numbers here. Your range, once again, is y is greater than 0 on this one. We'll look at the try these in class. Let's keep going. So now we have a little bit different here because we've added a couple new options here. We've got not just raised to the x, but to the x minus 3, and then we've added this +2. But we're going to go through the same process that we were doing before. We're going to create that table of values. Okay. Now, in this particular case, you might have to adjust what x values you use because you might not get the full shape of the graph here. But again, just plug in x values. So let's create our table of values here. X and y. I'm going to still use -2, -1, 0, 1, and 2. And again, just plug it in and see what you get. You get a y value of 2.125 here, 2.25, 2.5, 3, 4. I'm going to go one more. 6. Okay, so let's take a look at this graph. Just plotting the points. 2, 4, 3, 6, and then the next one was 4, 10. So you can see, that's why I wanted to do a couple more here. What our graph looks like here. And again, use the calculator to just plug in those x values. You could even use Desmos to help you, but we do want to see a table, okay? But you want to see what that graph is looking like. And most importantly, let's describe the domain and the range. Like usual, your domain is all real numbers. I can plug any number in for x. But take a look here. Here, my graph really never crosses this line, this imaginary line right here. Well, where's that imaginary line? It's at 2. Notice it's at this value right in here. So if we take a look at that, okay, our range in this case would be y is greater than 2. And if you took a look at the table, you could see that it gets close to 2, but it never actually reaches that value of 2. And again, like I said, you can use Desmos to help you graph these, but make sure you're comfortable with describing the domain and range and creating that table of values. We'll save this one for class, as well as the word problem here. Again, just to recap with exponential graphs, what we've talked about today. Remember, exponential graphs have a constant factor, so we're being multiplied our y's by the same amount each time. Make sure you're comfortable with being able to evaluate by plugging that x value in. You're good with the graphs of exponentials. You're able to describe the domain and range. If you can do all of that, you're good with this section. See you in class, guys.